We're going to finish up our discussion in Chapter 6.3 dealing with orbital hybridization by creating somewhat of a table so we can think about how hybridization might be formed for atoms in which all atoms are involved in single bonds. And we're looking at the possible hybridization about a central atom. Beryllium hydride. Remember, we said that beryllium is an exception to the octet rule. It only needs 2 regions of electron density about it. So in other words, beryllium has 2 electron domains. When an element, our central element, has 2 electron domains, we're going to say that there's a possibility that it's sp hybridized. Let's just go through one more example of how we can visualize this using an orbital diagram. If we think of beryllium and we look at its orbital diagram in terms of energy, beryllium has 2 1s electrons and it has 2 2s electrons and it has 3 empty p orbitals. 3 empty 2p orbitals. Remember, they're 2p. So what are we suggesting by this model? We need to have two bonds that are situated at 180 degrees from each other, and they have to be identical. They have to be the same type. They have to have the same energy. So what happens here is that we're going to mix 1 part S with 1 part P, and we end up with an sp hybridized orbital, 2 of them, with 2 electrons from the 2s. We sort of promote it and we bring one of these down in energy, and now we have an sp hybridized orbital. And what we end up with on beryllium is we have these 2 lobes that are going to interact with an electron from hydrogen, such as that. So we can think of that's what's happening in beryllium. So when we have 2 electron domains around our central atom and they're all involved in bonding, we have a linear geometry and we're expecting to have an sp hybridized central atom. Let's think about electron domain geometry and how important that is to help us make our predictions. So as we just showed, for beryllium hydride, get a better marker. Two electron domains, and they're all involved in bonding. So it's linear geometry. And we expect sp hybridization. Another particular example of a molecule, remember, BF3. If we think of BF3, we have a central boron, 3 electron domains about the central boron. So therefore, we need to have 3 equivalent orbitals. This will be sp2. 2 parts P, 1 part S. That accounts for the equivalent 3 orbitals surrounding our central atom. So another way you can think about it, we can add up these subscripts. Remember, we said if we have something like methane, CH4, we have carbon bonded to 4 hydrogens. We need 4 equivalent orbitals, and we said we end up with sp3, 3 and 1. Now remember, we did say that you can have lone pair of electrons as long as we're all involved in single bonds. We showed once again that water had sp3 hybridization. Let's look at ammonia, NH3. Ammonia needs 4 equivalent regions about itself. 4 equivalent. 3 of them are bonded to hydrogen. This lone pair of electrons have to be in an equivalent orbital. NH3 also adopts sp3 hybridization, and that's because the electron domain geometry is identical to CH4. Both of them have a tetrahedral electron domain geometry. So the big thing, and when we're predicting orbital hybridization about our central atom, is the electron domain geometry. Very important. So let's think about, continue our table. BF3, sp2, CH4, and NH3 were both sp3 hybridized. How about central atoms that have an expanded octet? Well, this is the idea that we said that some people are debating. We do have d orbital availability. Let's think about phosphorus pentachloride. We drew this molecule earlier, and as you recall, we said we have a central phosphorus with 5 chlorine about them. And if we drew the Vesper geometry to the best of our ability here, there's a chlorine. We should recognize that phosphorus requires 5 equivalent orbitals about itself. This is where we're going to borrow a d orbital. We're going to take one of our s orbitals. We have 3p that we can add to this hybridization scheme. And we can take a d orbital. So let's just think of how we can arrange these in terms of the superscripts, the exponents on these. 3 parts p, 1 part s, 1 part d. How many bonds do we have around the central phosphorus? 1, 2, 3, 4, 5. And they have to be equivalent. So we're going to hybridize 1s, 3p, 1d. We have 5 equivalent orbitals. Notice how we can add those exponents for each of those orbitals that we're adding into the mixture that we're making. Let's look at another example. Again, the electron domain geometry helps us to make this prediction. If we have an electron domain geometry that's trigonal bipyramidal, such as phosphorus has, we're going to expect an sp3d hybridization scheme. Let's try one more. Xenon tetrafluoride. Let's think about what kind of hybridization scheme we're going to need. And remember, xenon is an inert gas. So if we have our central xenon and we're going to have 4 fluorine about it, and we're going to have bonds, and let's remember our valence electronic count. I sort of got ahead of myself. Xenon has 8. There are 4 fluorine. Each of them have 7. 4 times 7 is 28. We have 36 electrons to work with. We've used up 32. Remember, xenon can have an expanded octet. We can put 2 electron pairs. Total of 36 electrons. Remember, we said the predicted geometry is based upon the electron domain geometry. When we have 6 regions around our central xenon atom, we're going to put 2 electrons on the axis above and below, and we're going to fit our fluorine in a square planar arrangement around our central xenon. So let's see, how many equivalent orbitals are we needing to meet this geometry? Remember, it has a electron domain geometry that's octahedral. So we need 1, 2, 3, 4, 5, 6. Notice the lone pair of electrons have to go in equivalent orbitals also. We need 6 equivalent orbitals. Let's think of our hybridization scheme that we can work with. We can hybridize an s, and we can also hybridize 3 of the p orbitals on our xenon. So right now we have 4 equivalent orbitals, but remember, xenon also has available d orbitals. We can borrow 2 d orbitals. So notice this has an octahedral electron domain geometry, and we would expect or hypothesize that the possible hybridization to meet these equivalent orbitals will involve 1 part s, 3 part p, and 2 part of the d orbitals that xenon has. And remember, we said that that was one of the ideas behind why inert gases can participate in bonding. They have available d orbitals, and they can be involved in the hybridization schemes that we're predicting based upon valence bond theory. So that's it with dealing with single bonds and central atoms with lone pairs of electrons. Our next lecture on Wednesday will involve the multiple bonds, and we'll be getting into more of that in our next discussion. Thank you.